a junior at Cape Coral High School in Cape Coral, Florida. My research focuses on finding the optimal tuning system for playing music. Creating a tuning system, or the system that determines what pitches to use when playing music, is complex. We don't want to create music with very few notes. However, adding more notes leads to conflicts, as every combination of pitches cannot be tuned perfectly. When a string is plucked, we hear a frequency spectrum that consists of a fundamental frequency, along with a series of higher and pitched and fainter overtones / partials. I'll demonstrate the existence of this partial by playing on the piano. First, I will silently press the C4 key, allowing it to freely vibrate. Then I will strike the fundamental frequency C3, which will resonate the C4 string, consequently producing the sound of a partial. A tuning system's goal is to provide a consonant musical scale where the frequency spectrums between notes coincide, meaning that partials perfectly align with each other, creating consonants. Piano strings have a degree of stiffness, causing the partials between notes to misalign, resulting in inharmonicity when two tones are played together. To fix this issue, a tuning system must slightly stretch the spectrum, allowing overtones to coincide, consequently minimizing dissonance between two tones. My research begins by deriving the wave equation for an elastic string, and I apply the separation of variables method to solve a second-order partial differential equation. The motion of a stiff piano string is modeled by the Euler-Bernoulli beam equation, a fourth-order partial differential equation. Solving this equation using the same method as the elastic wave equation results in the formula for the stretch frequency spectrum. Using Python, I modeled the dissonance curve of this frequency spectrum and calculated the sensory dissonance of 3 alternative tuning systems constructed from the partials that make up the octave and fifth intervals.